There we go. All right. So let's take a look at this one. There's a couple different ways that we can think about this. Depends on how much we remember about special right triangles. And that's geometry. There we go. Okay. So there's the special right triangle method of remembering this and noticing that we're dealing with a 30, 60, 90. So either way, we should be able to figure out that this angle is 30 degrees just by knowing these two, right? Because we know this one is 60. So 90 minus 60 gives us 30 for angle X. All right, and then finding the sides, we need to find WY and XW. So knowing that this is the hypotenuse of a 30, 60, 90, you can just divide the hypotenuse by 2 to get that side, to get the short side. And then you can multiply it by root 3 to get the longer side. But if we did not remember special right triangles, that's okay, because you can still use right triangle trig to do this instead. We could know that since this angle is 60 degrees, the opposite side, the adjacent side, and the hypotenuse. So since we're given the hypotenuse, we're going to use sine and cosine to set up equations. We can go sine of 60 equals opposite over hypotenuse. So we'll just call that variable x for a moment. And we'll call this one y. X over 20. And then we can go cosine of 60 is y over 20 since it's adjacent over hypotenuse. And then all we have to do is multiply by 20 on both sides. And then into your calculator, you would type 20 sine of 60. And you would get 17.321 if you rounded to the nearest thousandth, which is the same as 10 root 3. And then you would multiply by 20 on both sides here, and you would type in your calculator 20 cosine 60, and that would give you that y is 10. So then this would be that 17.321 if you were rounding instead of getting the exact answer. And then this one is still just 10 because that is your exact answer as well as your rounded answer. Okay, so there were kind of two different ways that you could do that one if you want. And again, you can pick either way. If you were doing it for an IXL section, they would expect, if you were doing it for the IXL section from the pre-calc version of things, they would expect your answer to be in this format here. If you were doing it on the geometry version of things, they would expect your answer to be 17.3 because I think they were rounding the nearest 10th. Anyway, that's kind of what we did yesterday in a nutshell. We also talked about secant, cosecant, cotangent stuff. Your calculator is giving you another answer, probably. So the issue with that is most likely if you're in degree mode or radian mode. So if you've got a TI 84 type of calculator and you go to mode and you go down to here where it says degree and radian, you want to make sure that that degree is highlighted for the right triangle trig problems anyway. As we move further along, we'll start putting things into radian mode instead. But for today, we're sticking around in degree mode. So make sure that that's the case. Also, Desmos may or may not be in degree or radian. I don't remember what the default is for that. So if you were using Desmos, that could also be happening. I'm pretty sure their default is degree, but I can't remember. Yeah, so that always generates all kinds of fun answers when we start going back and forth a little bit more. So yeah, always double check your calculator mode. Cool. Okay. So for today, let's see. We're doing some of the same and some moving along. We're gonna deal with more right triangle trig, solving triangles and stuff like that. You do a little bit more just general guided practice with that. And then we're also going to talk about converting degrees and radians back and forth. So time for some notes. So 4.1, 4.2, we're getting just barely dipping a toe in 4.2 today. Right triangles and degrees and radians. Okay. Let's see. Do we want to start with that? Yeah, let's do it. Okay. So we're going to start off with, this is a slightly different style of problem, but very similar to the one that the ones that you did in M5. So we're going to be given that sine of theta is 5 over 13. Find all 6 trig ratios. Okay. So we might have seen a question similar to this in M5. We might not have quite gotten all the way there. But given that sine is 5/13, find all 6 trig ratios. So we know from yesterday and from hopefully past years as well that sine is opposite over hypotenuse. So we're going to start with that. We're going to build a triangle here. So for now, just draw any generic right triangle. I'm going to draw mine like that and put theta in the corner. And so we know 5 over 13 is going to be opposite over hypotenuse. So the opposite is straight across over here. The hypotenuse is right here. How can I find my third side real quick? Or does anyone recognize this triangle and know what it's going to be already? Nice, Ryan. Yeah, it's going to be 12. There's a couple ways you can do that one. You can remember that it's a Pythagorean triple, the 5, 12, 13 triangle. Or you can use the Pythagorean theorem and just go 5 squared plus b squared equals 13 squared and solve it real quick. So we'll get 25, 169. Subtracting on both sides, we get 144. Square rooting, we get b is 12. All right, so then we're looking for all 6 trig ratios here. So we already have sine. We need cosine, tangent, cosecant, secant, and cotangent. Okay, so now that we have all 3 sides, go ahead and fill in the rest of the trig ratios. When you think you've got all your trig ratios, go ahead and type done in the chat. All right, looks like most people are finishing up there. All right, so remembering that cosine is adjacent over hypotenuse, we should end up with 12/13 there. And then tangent, opposite over adjacent, would be 5/12. And then for these ones, you can just flip them all. So cosecant would be 13/5. Secant would be 13/12. Cotangent would be 12/5. All right, the only one that's usually kind of a little bit difficult to remember is, or get mixed up with, is secant and cosecant, remembering that cosecant does not go with cosine. It goes with sine instead. So remembering that that's the case is usually the thing that trips people up a little bit. But once you get in the habit of remembering that it's kind of the opposite of what you would think, it's not too terrible. Okay, so that's another kind of problem that we could see involving our 6 trig ratios. The most common kind of problem that we're going to see, though, is just being asked to solve a triangle. So we're going to do that next. All right, for this one, we're going to be given a right triangle. And let's say that ABC, this side length will be 23, and this side length will be 16. Yeah, that's enough. Okay. So we want to find measure of angle A, measure of angle C, and the length of side AB. Okay. So to start with here, finding our missing side, we can just use the Pythagorean theorem. So we'll call this A, and then A squared plus B squared equals C squared. So A squared plus 16 squared equals 23 squared. And unless you have all of your squares memorized, you might want your calculator. And then we're going to go ahead and subtract 256 from both sides. And we get A squared is 273. And when we square root it, we get A is approximately 16.523. Or if you're looking for the exact answer, it would be just root 273. Since I don't think that breaks down any further. Let's see. No, because 91 is prime. All right. Yeah. One moment. Dog's barking. Okay. So now we've got our missing side. We just need to find our missing angles. Once we find one of the missing angles, the other missing angle is really easy to get. So let's say we want to find angle C. Well, the two sides that we're given as whole numbers are going to help us there. You can use the third side if you want to, but it's easiest to work with, or easier to work with these two numbers than it is with 16.523. So with respect to the angle that we're looking for, we know that 16 is the adjacent, and we know that 23 is the hypotenuse. So then if we're looking for the measure of angle C and we're looking for adjacent and hypotenuse, that's going to be cosine. So the cosine of angle C is going to be 16 over 23. And then just like we did yesterday, we're solving for that by using inverse cosine. So we'll take the inverse cosine on both sides to get that C is inverse cosine of 16 over 23. So on your calculator, it's usually a secondary function, secant cosine 16 over 23. And we get 45.921 degrees. And then if you really want to, you can find angle A in a very similar fashion. You can take the inverse sine of 16 over 23, or you can just go 90 minus 45.921. And that gets you 44.079 for angle A. And those would be all of our answers. Okay, so that's more of that right triangle trig. I think what we'll do is we'll move on to the last thing for today, which is converting between degrees and radians, and then we can come back to any of the others that we want to do more practice on. So with that, we're going to leave right triangle trig for a moment, and we're going to talk about degrees and radians. So first of all, I'm curious about how much you guys remember about degrees and radians. So on a scale of 1 to 5, 1 being like I've never heard of radians in my life, 5 being I'm a pro at converting between degrees and radians. How are we feeling? Go ahead and type in the chat. All right. We're in for a big refresher on degrees and radians then. And that's totally okay. I wasn't expecting, like, people to be super great at these because it takes a while to think in terms of radians, especially with the weird year we had last year. You probably didn't get quite as much in the way of degrees and radians as typical advanced algebra trig years. So here we go with degrees and radians. We're just going to kind of get an introduction today. Okay. So the first thing that we want to know about degrees and radians is that they're just both two different ways to measure angles. Radians are more related to arc length and things like that, and the radius of the circle, and I guess they're both based off of how much of a circle that you have. But anyways, there's some great conversion factors we're going to talk about here. The first one is we know that 180 degrees is halfway around the circle, right? It's a half rotation. And 180 degrees is pi radians. So that's one of our conversion factors. The other is that 360 degrees is 2 pi radians. or 1 full rotation around the circle. Okay. So we can express angles in degrees. We can express them in radians. In radians, you'll notice that most of the time there's a pi involved. Sometimes there's not, but most of the time there is. So when we convert between degrees and radians, there's 2 ways that we go. The first way is degrees to radians. And the second way is radians to degrees. And the great thing is this is just unit conversions. So if you are familiar with unit conversions from chemistry class at all, this is going to kind of take you back to that. If you haven't had chemistry yet, or you don't remember the unit conversions very well, then this is a refresher course. When you're converting degrees to radians, we want to use pi over 180 as our conversion factor. And then when we're converting radians to degrees, we want to flip that. And we're going to use 180 over pi. And that's mainly because if you're going degrees to radians, then you want the degrees to cancel out. So you're multiplying degrees by pi over 180 because you want the degrees to cross cancel. When you're going the other direction, radians to degrees, you want the radians to cancel out. And so you're multiplying radians by something over radians. So let's do a couple of examples here. First one, we're going to take 30 degrees and we're going to convert the degrees into radians. So all we're going to do is go 30 times pi over 180. Times pi over 180. And then we're just multiplying fractions. So 30 times, this is like 30 over 1. 30 times pi is 30 pi. 1 times 180 is 180. So technically 30 degrees is 30 pi over 180. The only thing that we get hung up on is that's not the simplest way to write it because that is not a reduced fraction. So we want to make sure we reduce our fraction. Both of these are actually divisible by 30. If we don't immediately recognize that, the first thing you can do is knock off a 0. And we get 3 pi over 18. And then we can notice that that's equal to pi over 6 if I divide by 3 on the top and the bottom. So this would be our simplified answer in radians. So again, all we did there was we set up 30 times pi over 180. And then we simplified what we got. Any questions with that first one? Any numbers we don't know where they came from? Okay. And then if simplifying fractions isn't your jam, I'll show you a couple different tricks we can use with calculators and things so that that's not what's tripping us up. But anyway, then we'll do one with radians to degrees. So let's do, we're going to take 3 pi over 2, and we're going to convert that into degrees. So we're going to go 3 pi over 2. This time our conversion factor is 180 over pi. So we're going to go times 180 over pi. And as we multiply our fractions here, the first thing we can do is cross cancel a few things. Like pi can cancel with pi. And then 180 and 2 can actually cancel because this will become 90 and this will become 1. So then all we're left with is 3 times 90, which is 270, over 1 times 1, which is 1. Now you can do this without that initial cross-canceling. You would end up with 540 pi over 2 pi. So if we didn't cross-cancel, I'll show that down here real quick. If I multiplied 3 pi times 180, you would get 540 pi. 2 times pi, you would get 2 pi. And then you can cancel at the end if you want to. So you would get rid of the pi's, and then 540 divided by 2 is 270. Either way, we should get 270 degrees. So you can cross-cancel at the beginning, you can cancel at the end. It doesn't really matter. But typically, you're not going to end up with, if you start with a pi on your radians, you're going to end with no pi. Any questions so far? Any numbers we don't know where they came from? Okay, let's do a few more. Let's get used to these. So this time we'll take something a little bit less common. We'll do, I don't know, 47 degrees to radians. And we'll do we'll go with 2 radians to degrees. Okay. So first off, going degrees to radians, we're going to use that pi over 180. So you can memorize this, or you can remember that you're trying to cancel the degrees. So the degrees should be able to cancel with one another, degrees in the bottom, degrees that you're starting with. So when we multiply these, we get 47 pi over 180, which I don't believe reduces at all. But this is where we can have some tricks that can help us check. Like that lovely math fraction button. So if you're using a TI calculator or a graphing calculator of some type, you can go 47 divided by 180, and then you can hit the math button, and then see that fraction is highlighted. Hit enter a few times, and you get that it is 47 over 180, and that is the simplest fraction that will make. You can also use, if you're using something like this that has math print on it, you can hit the fraction button right here and start off with 47 over 180. And then if it's simplified all the way already, it will tell you right here, or it'll tell you what it simplifies to. Or if we have a Desmos instead, I already got Desmos open, just kidding. We can run over to Desmos and go 47 over 180. And if you hit that button right there that shows up, it'll tell you what the simplified fraction is. In this case, it's still 47 over 180. But if I did like 2/4 or something like that, and I hit the fraction button, it would tell me 1/2 because I would simplify that to 1/2. So that's also another fun feature you can use to make sure you've simplified your fraction correctly. because we don't want that to be what we get stopped by. Okay. Then, going radians to degrees here. If we're going 2 radians to degrees, first off, we're multiplying by 180 over pi. And we're going 2 times that. So 2 times 180 is 360. And we have 360 over pi. That's technically the exact answer. Sometimes you'll be asked to round on these because 360 over pi degrees doesn't really make a whole lot of sense to us. So you could type into your calculator 360 divided by pi, and it'll give you a decimal approximation. So it's approximately 114.592 degrees. Okay. So I'm going to have you guys try some. This one will do 3 pi over 7 radians to degrees. And we'll do 426 degrees to radians. So go ahead and try those two. When you think you've got an answer, go ahead and type "got it" in the chat, and then we'll go over them. All right, Eduardo's got it. Labrielle's got it. Nice. All right, wait another little bit. Let's see if a few more people get it, and then we'll go over these. All right, make sure if you used 180 over pi for the first one and pi over 180 for the second one, those would be the correct conversions here. If you really wanted to, you could use like 360 over 2 pi or 2 pi over 360, but that would be a little bit pointless because it's just going to generate more reducing fractions for you. So anyway, looks like most people have it. So 3 pi over 7 times 180 over pi. You can cross cancel the pi's to start with if you like. 180 times 3 is going to give us 540, I think. Yes. Over 7. which gives us, let's see, if we're going to leave it as a fraction, it would just be 540 over 7, or we could have approximately 77.143. So if you got either of those answers, those will work. And then the second one, 426 degrees to radians. Multiplying there, we get 426 pi over 180. But that's not a very simplified fraction. We know that right off the bat because 426 and 180 are both at least even. So if we reduce that, you can reduce it in your calculator. You can start just thinking about what things would divide. You can go about it whichever way you like. We should get, I believe, 71 pi over 30. So I would just leave it like that. And that would be radians. Okay. So that's just a quick intro to degrees, radians, converting between the two. For today, especially, still leave your calculator in degree mode. That way, when you do the right triangle trig problems, you don't get different answers, since we're working in degrees on those. But before we jump into assignments and stuff like that, are there any particular types of problems that we want to go back to? Any that we want to, any particular kinds that we would like to see? Actually, here's what we'll do. I'll tell you what the homework's going to be, and then those of you who would like to stick around and do some problems with me, you can. And those of you who want to just go get going on the homework, you can do that too. So here we go. In Google Classroom, our homework for today, we'll also have an exit ticket today. We'll typically, for those of you who haven't had me before, we'll typically have a Google form exit ticket each day that you'll get points for doing. Just to kind of give me an idea of where the class is at. We're going to do M1 and M12 today. So we're finding an angle measure with our trig ratios, and then we are converting between radians and degrees. So the first set, trig ratios. Finding an angle measure is going to look a lot like just using those inverse sine, cosine, tangent to find an angle measures. Like, so for this one, angle H, the two sides that we are given are the hypotenuse and the adjacent. So that means we're going to use cosine. So we would take the inverse cosine of 10 over 10 root 2. And that would give you your angle measure. For the others, we're going to be converting between radians and degrees. So it'll give you something like 90 degrees, and it'll ask you how many radians that is. So for some of these, it starts off with pretty simple. It gives you some options of different radians that it could be. And then as we go through to higher levels, it starts asking less common angles and things like that. It starts asking you to give the answer to supply it instead of them supplying options for you and stuff like that, making sure that it's in simplest form and whatnot. Okay. And then the exit ticket for today. So the exit ticket, for those of you who haven't done one of these in my class before, is just a short, ask you to, like, how well you think you know what we did today so far. It asks you a question or two, and then like on math, and then a fun question at the end. Anyways, so we're at that point in class now where if you would like to stick around and ask more questions or do any of the questions on your IXLs with me, you can. If you would rather get going and start working on your own, you are free to get on out of here. Have a wonderful afternoon.